Okay, so hello everyone. So for today's webinar, right, we're going to talk about game theory. So we're going to go into the introduction of game theory as well as theoretical explanation behind the various game. That's what we're going to go through today. Okay, so this is the rough overview of what we're going to go through today. First, we have the introduction, and we're going to go through the overview of the terminology and as well as the various types of games. And on top of that, we're going to go through 5 other games, namely Ultimatum, Battleship, Prisoner's Dilemma, Volunteer's Dilemma, and the final one will be the Evolution of Trust. Okay, so we're going to start with the introduction of game theory. So what is game theory? Game theory is the study of mathematical models to study conflict and cooperation between rational decision makers. So rational decision makers are people who make decisions that maximize their own benefit. Okay, so where is game theory being applied or implemented? So in fact, it can be found all around us, including, of course, games, as the name suggests, public transports, like the transport arrival time, as well as economy or stock exchange, for example. Depending on the action of others, you can predict whether they would, for example, buy or sell to various degree. Okay, so how did game theory came about? So it started when von Neumann, in the picture, he realized that poker is not reliant on probability alone, but bluffing is also involved, which he wanted to formalize it. Hence, he worked with Oscar to explore his findings and implement his models in economic behavior. And hence he created this book, Theory, Games, and Economic Behavior. Okay, so now we're going to start on the various terminology as well as the various game types. Okay, so you should know that game theory, there are 6 points we have to keep in mind. The first 3 should be familiar with everyone. First, we need the game itself, the various players to play the game, as well as the strategy that the players take. The last 3 may not be familiar, so payoff. So it means the outcome when a player receives from arriving a particular outcome, like a reward, whether he received a penalty or gained something from it, from his certain actions. So next is the information set, basically the information made available at any given point in the game. And lastly is the equilibrium, where in a point of a game where both players have made their decision and an outcome is reached. So this is what equilibrium means. Okay, now we'll start with the various game types. First being simultaneous. So simultaneous is where multiplayer can act at any given time, like rock, paper, scissors. So multiple players can act at once. And next is sequential, which is the exact opposite. So it means that each player can make a move one at a time, like chess, which is a great example. Okay, next we have symmetric and asymmetric. So symmetric is usually short games relying on tactics alone, whereas asymmetric is where players do not stand equally, like they do not have the same foundation, like some may be at a benefit, some may not, just like sliding. Next, we have perfect information. So perfect information is where everyone knows what is happening within the game, just like chess, the players, the opponent position on the chessboard. Whereas imperfect information, similar to poker as well as Uno, that suggests in the picture, we do not know what the player hand has. So there's imperfect information. Next, we have cooperative. So cooperative means that you have teammates to work with, be it bots or not, just like Overcooked in this example, some of you may know. And non-cooperative, it means that you are playing alone. So you are a solo player. And this zero sum and non-zero sum. So zero sum means that a gain of a player is a loss of another, like on an even to an even degree. Yeah, so like if you gain a vote, so it's +1. If you lose a vote, it's -1. So that's zero sum. And non-zero sum is the exact opposite, where winning and losing is not equal on either side. And also, right, you can gain without losing anything. So like there's an overlap. okay, a good example is like a pirate and a cargo ship. So when the pirate is going to raid the ship, right? So if you raid the ship, manage to raid the ship successfully, so the pirate gain a lot of loot lah. So the ship loses. However, if the ship manages to defend itself, so nothing changes, right? The pirate loses, and the crew or the cargo ship just remain as it is. So yeah, so that's non-zero sum. I think you can get the idea around this. If you can't, you can just search on Google. They'll have a better explanation along the way. And the last part is the single shot and repeated. So single shot means it's only for one round. So the game is only being played once. So that's what single shot means. And repeated, it means that the game is being played over and over, like multiple rounds. So this is easily understood. So right now I've just covered the 6 various types of games. And now we're going to begin with the first game, which is the Ultimatum Game. So for those who do not know, right, Ultimatum Game is a game of empathy. So like, do not mistake it with sympathy. Sympathy is feeling for others, whereas empathy is feeling with others. All right, so let's begin. So I'll explain how this game works. So assuming that player A has $20 divided into 10 $2 notes, right? So he has to split this amount, be it evenly or unevenly, to player B. It could be more, less, or equal. So assuming that player A gives lesser amount to player B, so it's uneven. So the condition is this, right? Player B has to accept the amount that player A gives. So if they accept, both will get the amount of money that they agreed on home. However, if player B rejects this amount, both will get nothing. So both will get $0. Okay, so I'll jump straight through the diagram that explains how this works, assuming that proposer is player A and responder is player B. So the proposer could be fair, make a fair cut, like 50-50, so $10 each, so it's 50-50. However, if it's unfair, the responder can either accept the unequal amount, depending on how much they give, or reject, so they'll get none. So this briefly sums up the model for this game. And right now, I'll talk about the decision process. Okay, usually when the offer is fair, right, both parties benefit equally, and the offer is usually accepted. It also shows that an understanding that the individuals prefer equal outcomes over personal gains, and thus most people would definitely agree with this offer. However, this is also due to social norms that people are trying to adhere to. So when a shared expectation is met, people tend to agree with one another. However, when people deviate from these norms that I've just talked about, right, there's a change in behavior and people would tend to reject the offer and get nothing rather than something. So this is a form of punishment. All right, so this exactly sums up what the Ultimatum Game is. Yeah, it's definitely a fun social experiment. I guess you should try, or you can just research more on Ultimatum Game and discuss more about game theory. So I've finished discussing my part. So now I'll pass on the time to the next presenter who will discuss about the Battleship game.
So thank you, Colin. So hi everyone, I'm Shin Yun, and I'll be sharing about a popular game, Battleships, whereby game theory can be applied to mathematically prove the best strategy in winning the game. So what exactly is Battleships? Well, Battleship is a war team board game for 2 players in which the opponent tries to guess the location of their opponent's warship and sink them Maybe you and your classmates may have played the paper and pencil version of the game in school, and it's a game that heavily involves strategic planning. So how this game will be played will be that each player, A and B, will have a 10 by 10 grid, and each individual square may be identified by a letter and a number similar to chess. From there, players can arrange their ships and record the opponent's shots and their own shots. A player will have 5 ships of different classes. Each ship occupies consecutive squares on the grid, which will be determined by their type. Firstly, the carrier class, highlighted in green, occupies 5 spaces. The battleship class, highlighted in red, occupies 4 spaces. The cruiser and submarine classes, highlighted in purple, occupies 3 spaces. And lastly, the destroyer class, highlighted in yellow, occupies 2 spaces. So after the ships have been positioned, the game proceeds in a series of rounds, and each player takes a turn to announce a target square in the opponent's grid which is to be shot at. And when all of the squares of a ship have been hit, the boat will sink. So one rule players might have to take note is that the ships cannot overlap, such that only one ship can occupy any given square in the grid. With that being said, out of the 100 spaces on the grid, 17 spaces will be occupied by the ships. Players would then have a 1 in 5 chance, or 17% to be exact, of hitting in the first round. So what are the strategies that may be used? One strategy that may be uncommon among players would be targeting at locations with pure randomness. It involves a massive exercise in probability. A simulation by Nick Berry Data Genetics showed that over 99% of games will require at least 78 shots by using this random system. Making random shots would be really inefficient. Choosing all shots randomly against an opponent would cause the player to lose almost every time. Additionally, this strategy is not as easy as it seems, as humans are incapable of generating a random number sequence. So the next strategy we'll be looking at will be the hunt and target method, and it is a strategy used by most battleship players. The player will start by randomly firing shots, followed by working around the hit. Using a blend with the previous strategy of pure randomness, after a player gets hit, they will go up, down, left and right around the impact to find the next part of the ship. Hence, by repeating this strategy throughout the average game, it will take about 65 shots, which is much better than pure randomness, but still not great. So a slightly better strategy that players may use would be to hunt and target with parity, or some may call it as checkerboarding. This strategy is pretty straightforward. Instead of thinking of the game as a 10 by 10 grid, we should create a checkerboard on the grid and only fire on either the light tile or the dark tiles. We want to do this because every ship must have components on both types of a square. Take for example the destroyer on your right. As it takes up 2 tiles of space, the destroyer would have elements on both kinds of square. Hence, by only firing on either light squares or dark squares, the player would not completely miss any ships. This does for us because it will eliminate half the plays that we would have to fire at if we only fire on light squares or dark squares, and after which the hunt and target method will be used. Hence, using the hunt and target with parity method, the average game will take about 60 shots, which is better than the previous method but still not optimal. The most optimal strategy will be to consider each tile's probability on the grid for every round of each game. It considers the board and whether the ships of a certain length are likely to be in a particular board position. As we will have imperfect information at the start of a game, the best option will be to shoot in the center and adjust from there. This slide shows how a computer, through an algorithm, may consider the remaining spaces on the board and the likelihood of a ship of a certain length being in a specific position. Hence, it will give a probability of a ship present at a particular location as indicated by the so-called heat map. With every move made, the heat map would be updated and refined to suggest where the player should target next. Although we may not be as fast or as accurate as computers, humans can generate a reasonable estimate in our minds by employing each tile's probability on the grid and refining the sequence in our brain with every move. Hence, by guessing, recalibrating, and repeating, we will increase our likelihood in winning a game of battleships. Hence, using this strategy has a huge payoff as the number of shots will be drastically reduced to their 30s to 40s. So now that you have learned about the different game types and game strategies for Ultimatum and Battleships, we'll explore some famous game examples analyzed in game theory. So the prisoner's dilemma is one of the most well-known concepts in modern game theory. It is a paradox in decision analysis, whereby two individuals acting in their own interests do not produce the optimal outcome. The typical prisoner's dilemma is set up so that both parties choose to protect themselves at the expense of the other participant. As a result, both participants find themselves in a worse state than if they had cooperated with each other in the decision-making process. Consider the scenario whereby both prisoner A and B were part of a gang of robbers and were arrested for robbing a bank. However, the prosecutors have no hard evidence to convict them. The authorities have no other witnesses. Hence, to prove the case against them, the authorities will have to convince at least one of the robbers to betray his accomplice and testify for the crime. To gain a confession, officials had to remove the prisoners from their solitary cells and question each prisoner in separate chambers. Neither prisoner has the means to communicate and discuss with each other on their plans. So the possible scenarios that prisoner A and B may face are represented by this 2x2 box. Each prisoner A and B is faced with the choice to cooperate with his accomplice by being silent or to defect from the gang and testify for the prosecution by confessing. So if both of them cooperate and remain silent, they will only face a criminal charge of loitering. Both will be sentenced to 1 year each for prisoner A and B. However, if one chooses to confess while the other does not, then the prisoner who testifies will go free and the other prisoner will be sentenced to 20 years in jail. Additionally, suppose both prisoners A and B testify against each other. In that case, each will receive a 5-year sentence due to their contradicting statements. So what can we learn from this? As both prisoners do not know each other's decisions, and defection always yields better payoff than cooperation regardless of the other player's choice, it is a dominant strategy. The dilemma is that although mutual cooperation yields a better outcome than mutual defection, it's not the rational outcome because the choice to cooperate from a self-interest perspective is irrational. Hence, the equilibrium suggests that both players will make the best move for them individually, but worse for them collectively in the prisoner's dilemma. So the prisoner's dilemma has many real-world applications, including pricing strategies for business and even arm races. For example, both countries are better off when they cooperate and avoid an arms race, yet the dominant strategy is to arm itself heavily. So next, I'll be talking more about the volunteer's dilemma. So in the prisoner's dilemma, we have learned that each player has two options, cooperate or defect, similar in the volunteer's dilemma. Each player also has two opportunities to volunteer or remain silent. The volunteer's dilemma is a game mode in which player can either make a small sacrifice that benefits everybody or instead wait in the hope of profiting from someone else's sacrifice. And because the volunteer receives no benefits, there's a higher incentive for free riding than to sacrifice oneself for the group due to the bystander effect social phenomenon. Hence, if both players and other party does not volunteer, the worst possible outcome will be obtained for all participants. So this is a model where if you cooperate, there's a 0 chance, but if you defect and at least one other person cooperates, there's a benefit of 1 point, and if both defects, there will be 0 and -10 if both chooses to defect. So now I'll pass the time back to Colin to talk more about our next segment.
Okay, thanks, Shirin. So now I will cover the final part of this presentation, which is evolution of trust. So welcome back. Okay, so I'll just close this tab. Okay, so this is the evolution of trust. All right, you can Google this out in case it's not me/trust. I'll just paste it inside the chat later. Okay, so basically Evolution of Trust created by Nick Case. So this is based on game theory. Wait, let me define this. Okay, so the inspiration of this game, right, is basically during World War I, about like 100 years ago. So there's a strict orders, right, between the British and German soldiers, right, not to chillax with the enemy, like because they're enemy, so don't chill with them. So yeah. However, on Christmas Day, around between those dates, both sides left their trenches and crossed no man's land, and they buried their dead, exchange gifts, and play games. However, like 100 years later, right, in 2017, like the Boers has been at peace for like several decades. So yeah, so they decided to do this survey, like they find out if people still trust each other, be it stranger or not. So you find out that more and more people do not trust one another. So that is the puzzle that Nikki was thinking about. So why even in peacetime do friends become enemies, and in wartime, like do enemies become friends? So he decided to use game theory to try to explain this distrust. Okay, so we'll just begin. Okay, so before we go on to the model to show you about the game, we're going to talk about each round, how it is going to be played out. Okay, so this is similar to Prisoner's Dilemma. Okay, you have me and another player. So for in this game, right, this game Evolution of Trust, each of these other player are going to have its own style of play, different pattern or different condition. So we're going to start with the first one. Okay, so both sides are going to put their coin into this machine. All right. So meaning that if they put their coin in the machine, they cooperate. However, if they do not, it means they cheat. All right. So if both sides put their coin in, right? If both sides, decides to cheat, so they do not put their coin in. So both will get nothing. So 0-0. No gain, no loss. However, right, if one of the player decides to cheat, for example, this guy with the blue hat, so decides to cheat, he will gain 3 coin, whereas the me who decides to cooperate, who get cheated, will lose the coin that he just thrown into the machine. It's similar on the other player, so yeah, similar. However, if both decide to cooperate, both gain, right? So both +2. However, like each side would not gain as much as if they decide to cheat and the other player cooperates. So I think you roughly get the idea. It's similar to Volunteer's Dilemma. All right. So we're going to go through some of the characters' playstyle. So we're going to decide if they are going to cooperate/cheat. So I guess I'll be nice. I'll just try to cooperate first and find out if they would change in their playstyle. Okay, so when I cheat, he still cooperates. Okay, let's cheat again. Okay. So that's that. So now we'll move on to the next character. You can find out how they will play out. All right. So it seems that whenever I cooperate, he cheats. So I can assume that he always cheat. Okay, so next character. Okay. It seems that whenever I cheat, the other player, the character, doesn't retaliate. So I can deduce that he always cooperates. Okay. Let's start by cheating. All right. Okay. So right now we are on to the last character. So we can find out how they will play out. So I'll try by keep cheating and see if they would like change the way they play. All right. It seems like this brown character is much special. Like he has his own play style. Okay. Okay, so now we're going to create a model. All right. So with the 5 characters we just went through, the blue one, if you remember, he always cooperate and and he would always copy what I did for my last move. So it's basically copycat. And next is always cheat, self-explanatory, always cooperates, similar. And next you have the grudger. So the yellow one, it means that he will keep cooperate. And when I cheat, right? When I start cheating, he would always cheat like this guy. However, the detective, right, he'll play in a pattern, cooperate, cheat, cooperate, cooperate. And if I cheat back after, he will act like copycat and copy my last move. However, if I cheat back, he will become a cheater and always cheat. So that is their playstyle. All right. So this is the model. So each character I'm going to play against one another. So right now we're going to find out, right, if which of the characters would stand to gain the most within one round. All right. So right now I'm going to assume that the copycat does win because it seems like a very good move. Okay, so now I'll skip towards the end. Then you can see towards the final result. So once every round is played, we'll find out that at the end of one cycle, the copycat indeed does win. So the reason is this, all right? So the golden rule is the reciprocal altruism. So tit for tat, live and let live. So that's why peace could emerge, right? World War One, because like you copy what they does. So because when you're forced to play a game, the same game with the same specific people, just like copycat, not just the same generic enemy over and over again, copycat doesn't just win the battle, right? It wins the war. So that's why it's dominant amongst the others. It doesn't let the cheater exploit it and is able to cooperate with the always cooperate, as well as the other two characters. So copycat stands to win more. Okay, so now we're going to go in depth on the model. So it's going to be more repetitive. So basically, after each cycle, like you just seen before, we're going to eliminate the bottom five, which is the losers, and duplicate the top five. Okay, so this is a more complicated model. So now we're going to find out who would triumph amongst the others. So you can see that overall corporate is predominantly dominant. However, we all can guess that they will be exploited by the all cheat. So I can say that copycat does win. And now we're going to play the game and find out who will be dominant. So I think we can tell that always cooperate will get exploited by the cheaters and will stand to lose. Yeah. So towards the end, I think everyone can guess that the always cheat, now lose. So like just now what I just said, right? The copycat does not just win the battle, right? It wins the whole war itself. Okay, because the copycats are able to work with one another because they copy each other's move. However, the always cheat will not be able to work with the copycat because both, if you recall in the coin machine, once you keep cheating, so you copy the last move, so both doesn't gain. So the always cheat doesn't win the game. All right. Okay, so now we'll add the other two character, if you remember, the detective and the grudger. So I think it's pretty obvious. You can guess that the copycat just win again. However, if you just saw, right, the grudger does stick around for a while, right? Because remember, the grudger will always cooperate and the copycat, right, would copy their last move. So they would like stick around a little longer because they are willing to cooperate. And that's that. Yeah, this is an example. If we start with one copycat, one cheater, similar to the first evolution model we just did, the copycat does come triumph. Okay, so now we'll move on to the last part towards the end of this evolution of trust. So what we're going to do now is about making mistakes, all right? So this is another factor we will consider in our model. So basically, this explains. So as you can see, he fell and unintentionally cheats, right? So because of that, right, the opponent or the other player, even though they are of the same pattern of play style, they will have this cycle of revenge because this player or player A makes some mistakes. Okay, so why we consider these mistakes, right? Because we are going to consider a human factor, so it's not going to be a robot, right? Okay, so to encounter this, right, we're going to add another 3 more characters, namely copy kitten, simpleton, and random. So random is basically you're going to play whatever is one, be it copycat, be it cooperate, or cheat. So it's random. Copy kitten is like copycat. However, like if he get cheated twice in a row, he will only cheat back. So this is one of the various ways that Nikki, the one who created the game, decided to implement. And the second one is the simpleton. So basically he will start by cooperating and he will cooperate back. And he will do the same thing as the last move, even in mistake. So he would make a mistake, right? So if I cheat back, right? If I cheat back, he will do the opposite thing as the last move, even if mistakes, even if it was a mistake. Okay, so now we're going to implement this tree in this model. So right now we're going to predict who is going to win with this 5% chance of mistakes amongst the players. All right. So I'm going to guess the copy kitten win. Okay. It seems that the simpleton does win at the end. All right. So let's find the explanation for that. Okay, since we are here. This is because, right, the simpleton is actually capable of exploiting the always cooperate. Yeah, so people start cooperating. So, but if the simpleton makes a mistakes and cheats, since always cooperates never retaliates, it will keep cheating them. So simpleton does come triumph at the end. All right. So now we're going to place the simpleton, copy kitten, and random into our model with copycat and on cheats. So we're going to predict who wins. So simpleton wins the previous round. I'll just have him as my bet. Oh, it seems simpleton does lost this game. Okay. Copy kitten wins this time, right? So the reason is that copy kitten is a more forgiving version of copycat and was the most successful in the end, right? Because copy kitten is so forgiving, right? It doesn't entirely wipe out copycat because it still cooperates with them. Hence, in a bit of miscommunication, it could lead to more forgiveness. Okay, so if you remember, right, copy kitten will only cheat back only if it's been beaten twice, like once beaten twice, right? So basically, this is the rule of copy kitten, and it wins in this model. All right. So for miscommunication, right, we're going to try out this model again, but we're going to in a different manner by changing its chances of mistakes. So for this time, we're going to increase to 30% and find out who will be dominant. Okay, it seems that the higher the chances, right, the cheater would normally triumph because player will make mistakes and the cheater was able to exploit. Okay, it seems that this is the case. It means that the lesser mistake does, always cheater is unable to exploit the other. So I guess the copycat does win when there's lesser chance of mistakes. Yeah. So usually when player makes more mistakes, the character that always cheats will definitely able to exploit it. So that is one thing to keep in mind. All right. So this is the sandbox mode. Okay. You can just skip ahead to point 7 or the part 7 of this game. You can definitely check out this game. So the sandbox mode, I won't dwell too much about it. So you can change the rules, like just now if I mentioned, the various terminology, as well as payoffs, increase consequences, and population. Yeah. So my challenge to you guys, whoever is watching, is try to keep all of these characters alive in the game itself. So that is one challenge. You can definitely experiment with other types of scenarios, and maybe it will surprise you the results. Okay, so now I will try to conclude this. So game theory has shown us three things, right? Repeated interactions is necessary to keep a relationship going. All right. So, but you definitely need the knowledge of possible future to repeat interaction before trust can evolve. So it's crucial. And next, possible wins, possible win-wins. So it's a non-zero sum game, if you remember. Both can win without losing at all. And where it's at least possible, any players is better off with a win-win scenario, just like copycat. If he cooperates and he cooperates again, yeah, that's win-win. And lastly, low miscommunication, like we just discussed previously, right? So when level of communication is too high, trust usually breaks down. Yeah, so the cheaters will always win, if you remember the models previously. Yeah, so that's that. So lower miscommunication is always better. So a key takeaway is that when the game, what the game is defines what the players do, right? So our problem today is definitely not about losing trust. It's about the environment acts against the evolution of trust. Okay. So, but as the game theory reminds us, right, we are each other's environment. In the short run, the game defines the players, but in the long run, it's us who defines the game. So that is one thing we should keep in mind. We have to build relationship, trust, find win-win situations, as well as communicate clearly. So these are the three things we should bear in mind when create, as in real life or in games theory as well. And that, so the code to live and let live. So this sums up what evolution of trust is. All right, I let the credits roll. Nikki Case at least evolution. Yeah, so the case also creates plenty of other games related to game theory. Yeah, you can definitely check out his website during his free time.